I'm going to show you how to create the shorthand electron configuration as well as an energy diagram for any elements on the periodic table. So we'll start by looking at the periodic table itself, and the first element that I'm going to show you is beryllium, which is number 4 over on the left hand side, an alkaline earth metal. So typically beryllium has a fairly short electron configuration because it's so close to the top of the periodic table. However, it's a good example to show as the first one to show the shorthand electron configuration. So beryllium is the longhand electron configuration. We'll start with that, is 1s2, 2s2. So going back to the periodic table, 1s2, 2s2 is beryllium. Well, what you can do is, for the shorthand notation, is you find the noble gas that came before the element. So you back up the periodic table. So the noble gas that I run into is helium. So helium came before beryllium, and so what you do is you start with the noble gas. So instead of 1s2, 2s2, you start with helium, whose electron configuration is 1s2. So this right here is helium. So instead of writing this, you write the noble gas, and then you proceed with the configuration. So the shorthand notation for beryllium is helium 2s2. So this kind of seems silly to do for a smaller element. Let me show you how much time it saves for a larger element like vanadium. So vanadium is number 23 on the periodic table. So the first thing I'm going to do is find the element in the noble gas column that came before vanadium. So I'm going to backtrack to row 3, and the noble gas is argon. And then I'm going to start my configuration from there. So I'm going to write argon in brackets, AR is always in brackets, and then I'll start my configuration. So after argon, I am now in 4s2, and so that gets me 4s2, and then vanadium is the third element in on the D block, so then it would be 3d3. So you can see it saved actually a lot on vanadium because I was able to skip over argon, all the way up to argon. So for strontium, this one's even longer. So strontium is in row 5, and so what I'll do is I'll find the noble gas from row 4, so that would be krypton, and then I'll start my configuration from krypton. So then if I'm at krypton, I then go to 5s2, and then that's it, I'm at strontium. So my noble gas configuration, or my shorthand electron configuration, would be krypton 5s2 versus writing out the entire electron configuration. So again, shorthand electron configuration, you find the noble gas from the row above, and then you start your configuration. So let me do one more that shows a longer one. So let's pick silver. So if I'm going to pick silver, again, I want to find the noble gas from the row above. So I'm going to go to row, because I'm in row 5, I'm going to go to row 4. So I'm going to pick krypton. And then after krypton, it would be 5s2. And then silver is in the D block, and it is 1, 2, 3, 4, 5, 6, 7, 8, 9 into the D block. So it's going to be 4d9. So my electron configuration for silver would be krypton, 5s2, 4d9. Again, it's a lot simpler when you just start with a noble gas. And that's all there is to shorthand electron configuration. Energy diagrams are a little bit more complicated. So I'm going to give you 2 examples on this, and what energy diagrams do is they show the placement and spin of electrons in each energy level. So if you think about it, electrons are negatively charged particles, and they don't want to be next to each other. And so when you have electrons in such close proximity, what they do is they actually repel and spin in the opposite direction. The way that we notate that is we have a spin showing that electron's spinning up, and then another arrow showing that the other electron is spinning down. And remember, you can only have 2 electrons per energy level, and so one of them will spin up and one of them will spin down. So I'm going to show you the electron configuration for an element and then show you how each of the electrons are spinning within the element. So let's pick magnesium, and then I'll show you chlorine. So magnesium is 1s2, 2s2, 2p6, 3s2. Okay. How I would draw this, what I'm going to do is I'm going to draw a line under each of these. Because in the P lobe there's actually 3 lobes, I'm going to draw 3 lines. There's the X lobe, the Y lobe, and the Z lobe. And then the S, remember it's a sphere and it can only hold 2 electrons, so it gets 1 line. And then my 3s2 is going to get 1 line as well. Then I'm going to put each of these electrons on the line as a spin. So in my first energy level, I have an s suborbital and there are 2 electrons. One spins up, one spins down. In my second energy level, it's an s as well, 2 electrons, one spins up, one spins down. Up comes first, then down. In my P, I have them fully filled 2 electrons per line for a total of 6. So I have an up and a down, an up and a down, an up and a down. 2 electrons only. And then in my third energy level, I have 2 more electrons, 1 up, 1 down. And that's how you create an energy diagram. That's magnesium. So let me show you another one that's a little bit trickier. Chlorine. Chlorine is 1s2, 2s2, 2p6, 3s2, 3p5. So this last orbital isn't going to be quite full. So again, I'm going to draw it exactly the same way. So an S gets 1 line, 1 line. My P's get 3 lines, the X, Y, and the Z. The 3s2 gets 1 line, and then the P again gets 3 lines. 1, 2, 3, X, Y, Z. Okay. So again, let's fill in with the electrons and their spins. So my S has 2 electrons, 1 up, 1 down. This S has 2 electrons, 1 up, 1 down. My P lobes are completely full with 6 electrons, so 1, 2, 1, 2, 1, 2, 2, 4, 6. My 3s2 gets 2 electrons, 1 up, 1 down. And here's the trick. This P lobe section isn't full. If it was full, that would be a 6. So I can have 2 electrons per line, but I only have 5 electrons, so there's going to be 1 empty space. This is how you handle it. Fill all up arrows first, then backfill your down arrows. Okay, so I'm going to fill my up arrows first. Up, 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 backfill, down, down. So these ended up being full, but my Z lobe over here ended up with an extra space like that. So I'm going to show you one more example of a D block energy diagram. Okay, so let's pick cobalt. Okay, so the electron configuration for cobalt: 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, and then cobalt is 1, 2, 3, 4, 5, 6, 7 in on the D block. You have to use full configuration to draw the energy diagrams. You can't use the abbreviated short electron configuration. I know a lot of you are thinking that and thinking, dang it. Okay, so 1 line for the S. There's another S. Here's my P's, X, Y, Z. 3s2 is 1 line. My 3p6 is 1, 2, 3, X, Y, Z. 4s2 gets 1 line. And the D block can have 5 lines because there's 5 lobes. So 1, 2, 3, 4, 5. Those are all my D blocks. All right. So starting at the top, 1s2, up, down, 2s2, up, down, 2p6, those are all filled in, so I'll just fill them all in. 3s2, up, down, 3p6, again, those are all filled in. So just go through and put them all in. And then 4s2, those up and down. So here's the tricky part. The same rule applies. You have to fill all of your ups first and then backfill with your downs. So I have 7. So I'm going to go up, 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 up for a total of 5, and then backfill 6, 7. So on this one, I have 1, 2, 3 open spots, which is exactly how the energy diagram should look. And that's all there is to energy diagrams.